All right, my name is Wolfgang Ryer. I'm the moderator for the research seminar series, and we're still on Zoom, but Emre and I were talking about, we hope it won't be like this for much longer. I'm just going to introduce Emre, and then he can go ahead and take it the rest of the way. This is Dr. Emre Tepe of URP in the DCP, and he's going to be talking about investigation of the spread of COVID-19 in urban and rural areas with indicators of socioeconomic and built environment. And I will give it over to you, Emre.
Thank you very much for the invitation and this opportunity, and good afternoon, everybody. So let me set up my presentation very quickly so that I can start my presentation. So I hope right now you can see my presentation. So just checking. Okay, perfect. So today I would like to present one of my recently completed research on COVID-19, and I would like to begin my presentation with a simulation that summarizes the spread in US. Sorry about that. So here we see the number of positive cases per 100,000 population at the county level, starting from January 21st to November 5th. As you can see on this simulation, in the early days of this pandemic, northeastern large cities were hit hard. However, cases began rapidly increasing after May across the country, expanding towards some even rural areas. But the narrative, this pandemic hit hard only large and dense urban areas, stayed the same. So in this research, I'm trying to understand that component in a better way. So of course we see everything on the map, but let's look at the temporal dynamics of it. So states with large cities like New York observed high number of cases in the early days. If you look at the figure on the top right on the screen, states faced with large number of positive cases in early days. However, they have done successful job to reduce the rates of this spread after they hit hard. On the other hand, the trajectory of spread becomes significantly changing in other regions, including many areas with low density after May. Especially south regions like Florida, numbers have been increasing rapidly for a while. More interesting, the Midwest region where we have also many less dense areas began confirming many new cases as we go into the pandemic in recent months. Another very important patterns that we observed last year about the death tolls in big and small cities. And there is one study looked at the first and second 100 deaths in the nation. And what they find out, it is really troubling. So when we look at the shares of deaths in 100,000 population, so small towns and rural areas jumped from 20% to 15% when we compare first 100,000 and second 100,000 deaths in US. So this really is showing a trend. This is not happening only in dense areas. Yes, dense areas to some extent look like dangerous, but also the spread rapidly occurred in rural areas as well. So just to go back to the main focus of this research. So the goal of this research is to investigate effects of indicators built and socioeconomic environments on the spread of the COVID. So we have been discussing the benefits come with the density in urban areas in our field. And so we in fact promote some level of density in order to provide reliable public services, mainly utilizing economies of scale. However, during the pandemic, most people began to think living in dense urban areas like New York City they will increase their risk of contracting this virus. I believe there could be thousands other reasons why they should move to less dense areas. As a personal anecdote, I grew up in Istanbul, Turkey, and I personally observe benefits and disadvantages of living in a large, dense urban areas. However, realities are different. We need to have these dense cities to maintain economic productivity and protect environments around the cities. Any actions to undermine this goal and this effort could cause a catastrophic outcome in terms of climate change and sustainability of our ecosystem. So in this study, I want to test if the density is a major factor in the spread of this virus. And I see some very dense cities in Far Eastern Asia are doing much better than US cities. So I suspect there might be some other factors play a significant role in this. Therefore, I began to investigate this spread in regards to relationship between built and socioeconomic environments in this research. So also we need to acknowledge another thing. So during the pandemic, as a result of public health restrictions, some of our behaviors has changed in the way how we travel and where we prefer to live. And according to Google Mobility Map for United States, less people visited retail activities, groceries and pharmacy, parks, transit stations, and workplaces, while staying at home activity increased significantly. And this is an obvious change. But also some, as a kind of an immediate reaction to such changes in human behavior, both work and education places, obviously. Possible migration movement from dense urban areas to suburban suburbs have been speculated, such as a case for New York City. But on the other hand, when we look at some initial data, and Bloomberg City Lab collected some information regarding that migration movement, so they basically concluded, based on their initial assessment, they don't see such a rapid or significant movement from dense areas to less dense areas. So in terms of data, and so I obtained a COVID data set using Florida Department of Health daily reports. And so I essentially using Python automatically obtain or digitize their report to get these detailed information. So one thing happened during the time, of course, every day their report is changing, updating, but especially after June 28th, they really changed the way how much information they shared. So they basically give up upon sharing individual information. So, but nevertheless, the one good news from in terms of modeling and analyzing the Florida case in more detail, they released a zip code level information in terms for number of positive cases. So using those data set, I was able to test what I was planning to do for this research. So, but of course, I need to also obtain some information about built environment. But before I jump into the built environment, I would like to just show you some snapshot of pandemic in Florida. So on the left, we see the possible positive cases per 100,000 population. And this is as of December 23rd. So, and you can also see the larger cities are located on the map just to see where we are, if you're also especially looking at the Gainesville. And on the right, you can see the historical trends at the county level. And you can see things have changed over time very drastically. And then we also see some period which things went slightly okay, still not acceptable, but things are, as of December 3rd, is not in the right direction. So, in terms of built environment characteristics, I used Florida two statewide parcel data sets. Florida statewide parcel data set includes parcel geometry, area, land use, and built units, and age of buildings. And using this data set, I derived many variables represent the characteristics in our built environment. And here I would like to show these variables. So I have some variables regarding the general characteristics. I have detailed information about residential parcels, commercial parcels, and non-residential parcels. But also, like, these are going to help us to judge the built environment side of it, but also the other important factor is definitely socioeconomic indicators. So in terms of socioeconomic indicators, so American Community Survey is a really good source. So they have extensive indicators about socioeconomic characteristics. So using them, I was also able to get a good picture about Florida cities. So here you can see the list, the number of variables I tested and used in this model. And then without going to too much details, I want to basically touch on the major groups. Like we have the demographic characteristics, education characteristics, household characteristics, and also we have a really detailed workforce characteristics. But of course, those two components, I assume initially going to play a major role, but we also have many things changing during that period. So then we need to have some sort of control variables. In terms of control variables, I'd like to introduce mobility change during the COVID, and also I want to have some level of understanding how was the mobility characteristics pre-pandemic period. So, and in this study, basically travel behaviors of people are incorporated using American Community Survey as a pre-pandemic representation, and Google Mobility data as a pandemic or during pandemic representation. So you can also see the level of information I included in this research in regarding this component as well. So, and before I jump in the methodology, I must also tell you one additional component I included is mask rule. Basically, some counties have some kind of restrict regulations. Starting some certain dates, their dates are changing. So I also tested that component in the model. Plus, not every county experienced the COVID at the same time. If you remember, Miami started. I think Tampa the first one. Then Miami is the Orlando, and Miami is this followed Tampa, and I also introduced that spreading. Taking time over these zip codes in the model as a control variable. So, and in terms of methodology, and one of the obvious fact, what we see here on this histogram, so we have a number of positive cases at the zip code level. So in terms of, so what we have account data. And when you have account data as your dependent variable, we should definitely look for a discrete response model. And in regards, Poisson regression generally works well. However, there are some issues with the data and we need to address them. The first thing, we have some zip codes. We don't have any cases because one fact, there are not many people living, or some of them are basically purely wetlands or forest area. So this is a problem with working with Poisson regression. And then related to this initial one, the real problem is having this excessive number of zeros in the dependent variable. So an alternative solution to this, I consider a zero inflated Poisson regression. So when you have significant amount of observation, this one could work. But the problem is, even if this, I tested actually, so even if with this, so I still had the over dispersion problem, and then we need to solve that issue using a negative binomial model if you want to go to that route, basically using a discrete response model. But on the other hand, just going back and basically at that point, we step back and ask what we want to answer in that research, in this research. So my main goal is to understand what kind of factors play a role in terms of spread. And I'm not going to use this model for a prediction purposes. So then I basically, using a transformation, I can use an efficient linear model to achieve the same exact goal as I did, as I'm going to do with the discrete response model. So what I introduced in this research, instead of using a discrete response model, I transform my discrete data to a continuous data, basically taking the log of it. So then now I can work with some more efficient statistical approach. And also in this data, I have as initial sense, since COVID spread is physical, a thing, like basically we are talking about as we get close to the people, so then there is a chance we can basically spread this disease. So then when you look at in the community, the kind of a spatial relationship could play a role in this spread, and especially when you look at the zip code level, when you have a hot spot, and you are not surprising to see the nearby areas also a hot spot. So then we might end up seeing a spatial dependency in the data set. So not only I consider in that via just after having this initial thought in my mind, so not only included the linear model, but I also included some spatial regression modeling approach to overcome such an issue if I ever faced with it. So I basically used first order spatial autoregressive model and also first order spatial error model in this research. So, and again, as a modeler, this is my daily life. So I always start with a really basic setup, just to understand what's really going on here. So the major question and concern among the many people, like the density is the player. So then I ask myself, like, come up with this very simple model and only include density. The density here we are talking about population density, and also income could play a role. So I included too often, but then the model, I basically also ask myself another question. So do we expect to see a linear relationship, like a density is increasing and then a number of cases increases, or income is changing and the number of cases increases? So then what I did, I incorporated a nonlinear relationship, and I ended up getting a really high R-square with this simple model, and basically telling me density and also income a major player. And you can also see from this graph, as the level of income or density is changing, the impact is also changing. At some point it reaching a maximum level, but then after it's basically changing the direction, the sign of it. And then as you have more income, more density, number tends to go down, or rate of number tends to go down. So, but then I really asked myself, okay, the second question. So this simple model is good, but it's not telling me the entire story, because the income also density is also a product of some other small systems. So we need to look at those individual components. So then I decided to incorporate all these variables in a larger model, so then I can have a better insight about what is really going on in terms of community spread specifically. So, and since I have 50 plus variables, the first thing I did is essentially to test whether I have any kind of high correlation, because since I am right now in the process to create a linear regression model, it wasn't a good idea to have some variables highly correlated with other ones. So it is one of the major problem. So once I created this pairwise or computed pairwise correlation analysis, so you can see on the left, so some of the pairs turns out strongly correlated. So, and my initial reaction is basically to eliminate some of the variables which are highly correlated, basically exceeding threshold 0.7. So then these listed variables basically excluded from any further statistical models, because they are gonna essentially mislead me to a wrong conclusion. So I, as a starting point, I removed them. So then the next thing is, I am not an expert in the public health. So I am expert in basically modeling urban systems. So, and I have a clear mind. Basically, I want to use a statistical model, like they are really rational way to judge a system and understand from the data. And what I wanted to do, instead of just testing a couple of hypotheses, I basically tested any potential model and look for the best one. So using the linear regression model approach, so I tested all possible combinations and look for the best model. And you can see here on the graph only the adjusted R-squared. So we widely use adjusted R-squared to identify best model. Basically, high adjusted R-squared means your model explains the variation in your dependent variable very at that level. If it's high, which means very explains many things. So you have less unexplained one. So here even though we are not going to route, we are going to use that model to prediction purposes. So if we can achieve a high adjust R-squared, definitely it will put ourselves in a really nice position where we can say our analyses are robust and our understanding is really, really good in regards to what we are looking for. So, and if you look at the best model I identified using linear regression model, I achieved an R-squared, adjusted R-squared just over 0.9, which is a really a good level. If you are wondering how this is possible, because I have right now 27 independent variables and I have over 1,000 observations. So which is really those two are benefiting towards achieving such a high R-squared value. But of course, the story never ends. So the unit, once you have, in order to be able to use any regression model, you need to check if the assumptions are true. So one of the biggest problem I shared with you, so I had an intuition there could be some kind of spatial dependency in my data because of the way how COVID spread in the community. So then I looked at the essential residuals of my best model. And it turns out you can see the residuals on the map, and you can even visually judge this residual doesn't look like a random. And then, of course, I don't fully trust on my visual judgment, and I run a test using global Moran approach. And then it turns out I have a statistically significant spatial dependency. So then this is basically raise a flag and suggesting I should not continue working with this linear model. So then I'm going to enter the spatial dimension of it. And before that, I need to also consider what could be the better way to describe my spatial relationship. And I tested a couple of things, and then you can see here, I tested the number of K degree for this data set. It turns out 10 degree is the maximum spatial dependency. So then I need to use that peak value to achieve a more robust result. So here I would like to show the comparison of the model results. So I have three model tested. The first one is the SAR, spatial autocorrelation regression, SEM, spatial error model regression, and then OLS, basically the linear regression. So I have three candidates to choose from, and in this scenario, we basically discarded OLS because OLS cannot handle this spatial dependency. So we have two candidates among SER and SAR. So then I choose, I will have a test Lagrange multiplier, and SEM turns out the best one to fit this model. And if you look at it, we have only two variables, including intercept 3, turns out to be statistically insignificant. So those are regional shopping centers exposure time, and also the intercept. That's not a major concern. But if you look at the lambda, basically it is the spatial dependency component. It is statistically significant. So this basically shows a good a sign to work with such a spatial statistical model. So if we look at, for instance, the more detail about the SEM, so what we see, basically, we first start with the sign of it. And then many of the effects we incorporated in this model turns out positively associated, what does it mean? As we increase, for instance, single family residential density, also we end up seeing higher numbers in that zip code, so then zip code area. And we have only two variables. I picked the wrong one, by the way. Residential density is negatively associated, but the one, for instance, office, multi-story offices is positively associated. So just to summarize, many of them are positively associated, but a few of them are negatively associated. But the one very important factor here we want to understand, whether the density is the player, whether the built environment is the major player, or whether the socioeconomic environments are the major player. So of course, it is a difficult comparison to make because the unit what we have for the built environment is different than the unit what we have for the simple socioeconomic indicators. But if you look at the parameters itself, so what I realized, the built environment has a relatively less effective as compared to socioeconomic indicators. So this is a really interesting result. To some extent accepted, but this is definitely different than what the society assumed. So, for instance, I would like to highlight a couple of important things from these results. So, 1% increase in a ratio of people with healthcare support occupation in one zip code. Uh, uh, so we expect 10.5% increase in the expected positive cases per 100K population. So this, we are here talking about 10% increase by just increasing healthcare support of people who live in a zip code level. They are working in that occupation. So basically what this model is telling us, so they look like really susceptible, or they are under huge risk getting contracting this virus in this in this group of people. And also, this is not the most significant one. For instance, when we look at the other one is a percent rise in ratio of people with protective service occupation to population over 16, results in a surge nearly 23% in the expected number of positive cases per 100,000 population. And in this similar trend can also seen in people who work in sales and related occupations. The increase rate or effect is 12.5%, and also farming, whoever work in farming sector like farming, fishing, and forest occupation, their effect is 13.6, as opposed to, for instance, a built environment variable. Their effect is generally less than 1%. So this is really an interesting result, and then basically telling us the density itself is not the key. The socioeconomic composition is the major player. So then we should definitely focus our effort towards that that area. So I just want to summarize my research and our contribution to the field. So essentially, in this research, relationship between the coronavirus disease spread and indicators of field and socioeconomic environments in Florida have been comprehensively investigated, controlling mobility mobility behaviors and exposure times and mask rules county level. So this study indicates the socioeconomic indicators plays a significant role that organizes the built environments of the spread of this novel virus. And this study contributes to modeling coronavirus disease spread in the literature, basically testing various indicators of socioeconomic built environments. So I haven't seen any other studies, even that's something close to that. This one, providing robust estimates of controlling spatial dependency. So we have confidence about our result, and investigating a relationship at defined geographical unit that provide rich spatial heterogeneous information. So this concludes my presentation, but before I jump, thank you and give you a space for Q&A session. So I would like to introduce very briefly another fascinating research we are doing with my colleague, Dr. Abul Fazıl Safikani. He's an assistant professor in statistics. So we are basically working on a project which is going to contribute to UF AI initiative, and I want to share what we are doing here, and also take your attention towards this initiative. So in this project, we are working on developing a new approach, a methodological approach to deal with spatial-temporal modeling for large data sets like we have here in Florida. So in this research, we are going to work with a Florida parcel data set, which consists almost 9 million observations in it. And our main focus in this research is to using AI methodologies like neural network or machine learning methodologies like random forest, using their computational advantage, we would like to achieve such an unprecedented level of modeling. So then these are going to benefit to many expected outcomes in the field. So of course I don't have time enough to talk about this research, but what I would like to share with you, we are going to present our research in a more depth in the coming symposium, Hypergator Symposium on March 13th. So if you have time, please consider participating, because you can also see other people basically get award under UFAI Catalyzed Fund going to present their research in this symposium. So thank you very much for your time and attention, and I would like to give the room for your questions and also suggestions. Okay, maybe, okay.
Thank you so much, Dr. Emre. We appreciate it. I think your work it's obviously very timely with COVID. We're still kind of trying to get used to the whole landscape, and the fact that you already have such a robust study into it is really inspiring. Thank you so much.
Thank you. Any questions or suggestions? We have time, and I'm open to anything. So
I have a follow-up.
There is one question. Yeah, definitely.
That's me, Emre. I was just wondering, are you going to have a follow-up after December 23rd, 2020? And is that going to be part of your symposium where you're going to talk about that? Or are you going to apply that new big data to later than December 30 or 23rd, 2020 statistics?
So for that's a good question. So what I'm planning in terms of COVID case or COVID research. So I think this research study summarized the things in Florida really nice. But what I'm looking for, if I can get a daily count at the zip code level from the Florida Department of Health. So I want to go back and see the temporal dimension of this spread, because we looked at the accumulated number of cases as of December 13. So this is the basically time I said, okay, this is enough. We can definitely look at the relationship, but I don't have that temporal dimensions in the data. So what I mean by, for instance, we asked to stay at home before May 1st. I think, if I'm not remembering wrongly. So then before that period, potentially the things were different, but after that, during the summer, especially until October, things were different. But then after October, definitely we should expect a different scenario pattern, especially what could be really interesting after January, since we're getting people vaccinated. So then maybe we can also see and expect a different relationship, because of these players. They are mainly temporal. So this is one thing I'm willing to do, but I don't know if the department is going to release that data. So I tested this thing at the county level and at the even city level, but the number of spatial units is not allowed me to get a really robust results. So I really need to have at least zip code level to go to that route. Alternatively, I'm considering using a similar approach. I want to look at the national dynamics, because Florida itself is a good case. So we was able to look at the entire state without compromising any information. But potentially, when you compare Florida with California or New York or Washington, so things could be different because of there are other players going to be enrolled. One of them is humidity. So I read one research, basically humidity turns out to be an important player. It's actually helping for not to get contract with this virus. So I'm also willing to have one or two potential research in this area.
And will that be predictive also because you're using the ANN? Is that where you're going with it?
So for the AI methodology, I'm not considering applying here because one thing, we don't have too much information. So whatever we have is really manageable using statistics, and also the way how. So my research question is to understand from the data, and I want to be able to interpret my results efficiently and effectively. So AI methodologies and machine learning methodologies are really good when you want to have a predictive model, but they are not in that level for us to use for interpretation purposes. So then they are not suit what I'm looking for this research. But of course, for instance, our effort for land use change models, so they are really good candidates. So because initially I had a statistical based model, I was able to run using a supercomputer roughly 70,000 observation. Now we are in this research talking about 9 million observations, and we have a temporal lag. The temporal period is over 100 years, and then it is an extensive data set, and we definitely sure that's why we go to AI and machine learning basically way. And so then using their power, we will be able to manage to have a model at that scale.
Thanks, Emre.
Thank you. Anyone have any other questions?
Hi, Dr. Tepe. This is Connie. I
Hi.
find your research really interesting, and my own research also kind of overlap with yours. So I'm extremely interested in your research. And I just got 3 quick questions I want to confirm with you. Firstly is, I didn't get it very quickly, like how you use the Google mobility data of the people's mobility changes of the places of interest, because you raised this in the introduction part, and I didn't quickly get how you used this data in the following research. Did you use this in the transportation variable you used in the model, or used it anywhere else? I just want to know how you use this data.
Good. That's an excellent question. So I basically use it as an independent variable, but considering it is actually a control variable. So the reason I included that because American Community Survey provide us in really recent data as of 2019, but pandemic happened just after that. So then socioeconomic indicators, at least some of them has changed over time, and you can definitely see income is changed and mobility has changed. Unfortunately, I don't have control for income, but at least I had this control in terms of mobility. So I used it as if my control variable.
So for the change of mobility, you study the people's change of destinations. And do you also study like changes of travel distances or travel modes in this aspect?
I'm not sure if Google mobility data has that information. So basically what they have, they provide a number of visits and change comparing the baseline, which is basically a year before. So then you have these, and they are basically, and also they are providing that information either daily or weekly. I need to double check their reporting frequency. So every time when you look at one report, so the baseline is basically the year before. So then you can compare that change over time. So this is excellent. So basically I inputted that information, and since the data set I stopped basically December 23rd, so I used that exact time point as my anchor, so then incorporate in the model.
Okay, yeah, that makes sense. Thank you. I also got another question. So the residential density is also one of your results with a negative correlation. And I wonder if you use a residential density for every density variables in all the models. Because I recently checked the literature and it does say like residential density is a superior indicator over non-residential densities, and which will be easily affected by like economic agglomeration or some factors else. So I just want to double check.
Is it specifically talking, are they specifically talking about COVID spread? Or in general?
Yeah. I mean, the density variable, you only use the residential density. Is that
actually it's not the case. I didn't use only residential. So I also have commercial and non-commercial densities. So basically, instead of having a single density, I had multiple densities in the data set. But I eliminated some of them because they are highly correlated. Just to give you some insight about like how can be something highly correlated. So for instance, look at a downtown area. So where you have, for instance, retail activities and alongside office activities. So since both of them are highly dense in the same area, so then when you run a correlation analysis, they are going to be highly correlated. So this is a problem in many regression models. So you have to sacrifice one of them because what we look for in regression analysis, and that's why we are not going to AI or machine learning approach. So we purely have that individual effect. And then if you have a multiple or like a correlation or multicollinearity issue in your data set, you can't really have that individual effect. So then I remove some of them, but still I have and some variables other than residential about density. And if we look at, for instance, I have SFR, which is, let me see, SFR. I have this multiple story office, and this is I'm gonna tell this what it is in the table. I forget what the description.
Yeah, very specific. Yeah.
Yes, I have residential density, but if you want to see what I really included, so in terms of built environment density, let's put it that way. So here is the list. So what I included. So SFR, by the way, single residential, single family residential. So it is positively associated. So the other one is, let me see, restaurant. This rest density is the restaurant building density. So this is commercial one. So I had, and this multi-story office building. So all others turns out to be somehow highly correlated with the existing one. So I had to remove from the models.
Yeah, thank you.
And also, I'm just forgetting one thing. So the reason is not only the correlation. I basically forget one thing, because the one I removed because of correlation, basically I listed them here. So those are the ones are problematic ones. For instance, in terms of built environment, parks, grocery. These are not coming from the built environment, but let me speak. So this Emre story density, and these are basically come from built environment. The reason why I didn't have some of the built environments in the final model, because I tested like over 1,000 different combinations. And then in these combinations, what has happened, those built environment factors, some of them are excluded because they are not statistically significant. So best model all basically include mostly statistically significant ones. So that's why I had such a high R-square. So this basically tells us, so okay, the built environment and density is an important factor, but not everything. So definitely we have a single family residential units, it is positively associated, and restaurants are negatively associated. And my understanding is, since they are empty during that time, and then they are not, like, we basically ask people not to use restaurants during this pandemic. So when you have high restaurant density in one zip code, you see less positive cases, and also there are less people living in such areas. So that's also another potential explanation of this result.
Yeah, that makes sense. Thank you. Thanks for the detailed explanation.
Thank you for the question. Yeah. It's excellent.
Yeah, and I actually still have a quick one. So you also said the share of minority population has a negative correlation relationship. So I wonder if for different counties or cities, the concept of minority has different scopes.
So that's an excellent question. So actually, this is one thing. So I initially had some hypotheses, even though I said I am open to see the results when I have a robust model. So this look like is not matching what some other people speculated. But my understanding, when you look at the population composition in Florida, so minorities are generally less than 50%. And then what this model is basically doing, since there is not significant difference with even though when you look at the Florida Department of Health, so at some rate, so minority people has higher rate to contract this virus as compared to the other races. So then the issue is here with this model is not capturing it, because the way how we model is since their share is small and their number of positive cases is small comparatively, so we got that negative value. But this is something also should be investigated further once we have a new data set. And if the sign is consistent after we test it, because the sign turns out to be consistent among the trials, but once we add additional information, it could change. I suspect that. So then yeah, definitely we need to have a better understanding in that specific component.
Yeah, gotcha. Okay, thank you so much. That's all my questions. Thanks.
Thank you.